So, hi everyone. My name is Elshan Baghirov. I'm PhD student from Institute of Information Technology and data scientist from Capital Bank. Let me present the outline of this presentation for you. Firstly, I will provide information about malware and its effects. Next, I will discuss trends in malware. Subsequently, I will delve into the various existing methods for malware detection, highlighting their advantages and disadvantages. Following that, I will cover the topic of using generative adversarial networks for malware detection, addressing challenges, and concluding with a comparative analysis. Malware, short for malicious software, encompasses a broad category for software, specially designed to harm or exploit computer systems, networks, and users. These programs are created with malicious intent, ranging from stealing sensitive information to disrupting normal computer functions. Malware can take various forms, each serving a specific purpose in the realm of cyber threats. The several forms of malware exist, each posing distinct threats to digital security. Among them are viruses, trojans, worms, ransomware, etc. These malicious entities are designed to compromise computer systems, networks, and user data, demonstrating the diverse tactics employed by the cyber attackers. The AFTES Institute registers many malware samples in real time and visualizes the current situation in a website. And the second column chart shows the amount of malware and potential unwanted applications each year. Unfortunately, the numbers are growing up each year, and that's not good news. Next, we have a funnel chart. It helps us to see how fast we are detecting malware, whether it's per second, per hour, per month. Numbers are pretty high. It's a big challenge for us. Lastly, the donut chart tells us which operation system is getting targeted the most. Windows operation system at the top with the 97% share. So these charts tell us that dealing with malware is getting more and more important. Primarily, there are two methods for malware detection: static analysis and dynamic analysis. Static analysis is a method of detection malware by inspecting the source code of a program without executing it. However, the dynamic analysis involves detecting malware by executing it in a virtual environment. Each of these methods has advantages and disadvantages as well. So the static analysis is fast and exact. Exact means that this method ensures the precise identification of known malware, enhancing accuracy in threat detection. Secure means that static analysis provides a secure examination of files without executing them, reducing potential risks. But this method is unable to resist obfuscation methods. Obfuscation methods means the polymorphism, metamorphism, packing, etc. Weak automation means that in the static analysis, weak automation is limited, requiring manual intervention for comprehensive results. Zero-day malware, this approach proves less effective in identifying and mitigating emerging zero-day malware threats, require coding skills. Implementing static analysis demands coding skills, adding a barrier to accessibility. On the other hand, dynamic analysis overcomes the weakness of static analysis, effectively handling obfuscating threats and adapting new script to the new risks, but provides less interpretable results, requiring more time and resources and facing challenges when malware hides within the environment. A brief overview of generative adversarial networks-based malware detection is presented on the left side. And the main structure of generative adversarial networks has been shown in the right side. The main objective of generative adversarial networks is to acquire knowledge about probability density function and make estimates about the distribution of the training dataset. The generative adversarial networks are composed of a pair of neural networks known as the generator and discriminator, which undergo training simultaneously through a minimax objective function. You can see the formula of the minimax objective function of this method. The generator's primary role is to create synthetic data samples that resemble the real data that it has been trained on. It takes random noise as input and generates data in a way that is indistinguishable from the real data. By continuously improving its ability to generate realistic data, generator aims to deceive the discriminator. While the discriminator's main task is to differentiate between real and generated data, it evaluates the data it receives and assigns a probability score indicating the likelihood that the input is real or synthetic. The discriminator aims to become more accurate over time in distinguishing between real and generated data. The interaction between the generator and discriminator is adversarial, hence the name generative adversarial network. As the training progresses, the generator refines its ability to create realistic data to fool discriminator. And after a comprehensive review of existing literature and research, a number of studies on the generative adversarial network-based malware detection have been examined, revealing the principal limitations outlined in this presentation slide. I highlighted methods, solved problems, and also drawbacks of these methods. And I highlighted the main challenges and consideration in this slide. These challenges and consideration play a crucial role in understanding the broader context of generative adversarial networks in the field of cybersecurity. So let's say data availability. The generative adversarial networks typically require large and diverse data sets for training. Obtaining such data sets for malware, especially real-world zero-day and polymorphic samples, can be challenging. Imbalanced data means that malware detection datasets often suffer from class imbalance, where benign samples significantly outnumber malicious ones. The generative adversarial networks can struggle to generate realistic minority class samples. Feature engineering problem. Extracting meaningful features from malware samples is a non-trivial task. Generative adversarial networks may not inherently capture the most relevant features for accurate detection. The evaluation metrics, let's say, that determining the effectiveness of generative adversarial networks, generated adversarial samples, and their impact on malware detection models requires the development of suitable evaluation metrics. Resource intensive. The training and deploying generative adversarial networks can be resource intensive, both in terms of computational power and time, which may not be practical for all security settings. And the integration of the generative adversarial networks into the cybersecurity has demonstrated both promise and complexity. And generative adversarial networks hold the potential to revolutionize the malware detection, moving beyond the limitation of traditional methods like static analysis and dynamic analysis, especially signature-based methods. And the use of the generative adversarial networks can introduce ethical and practical considerations as the line between legitimate research and potential misuse becomes increasingly fine. And thanks for your attention.
Спасибо за доклад. Есть вопросы?
Am I right that a GAN is a kind of sandbox to reveal possible malware?
No, generative adversarial networks. Am I right? Your question is that the generative adversarial networks is virtual environment. Could you please repeat your question?
Is it a kind of is it used within into the sandbox, or it is a kind of more intellectual?
No. It is generative adversarial networks is different from the virtual environment. We use the virtual environment for the execute malware in the dynamic way. Before giving our malware images into the generative adversarial networks, we should prepare the initial malware samples. For extracting malware samples, we need to use some virtual environments like sandboxing or virtual machines to execute some features from the malware. After extracting features, we convert these features we convert executable files data into the images. After resulting these images, I will give these images into as the input of the generative adversarial networks. We can use generative adversarial networks separately.
Okay. Thank you.
Thank you.
Any other question? Then one more question. Am I right, again, am I right that this approach is used to analyze application which is going to be deployed on, for example, some cloud infrastructure before their usage?
The main idea is to using generative adversarial network is that we need more samples for the model training. Sometimes our data in the training is imbalanced. You mean that? So let's say our benign samples is more than the malware samples. Sometimes we have lack of the existing data sets for the model training. For this reason, we use generative adversarial networks to generate synthetic malware images for the refine our model for classification.
So it is used to train antivirus software, or to detect malware application.
Yeah. We can say that it is something like the differentiate malicious software as the malware, as the risky or safe data.
Okay, thank you.